So question 6 now has an endothermic reaction for a change, because the temperature at delta decreases by 1.3 degrees C. If the temperature decreases, that means that heat is being taken in to the atoms, molecules, ions, whatever, from the surroundings, so the surroundings cool down. So the temperature decreases by 1.3 degrees C. So the answer to A is that it's an endothermic reaction. So we can then calculate in B, Q equals mc delta T, the usual thing. And M, remember, is the mass of what's being heated up. So what we end up with is a solution of sodium hydrogen carbonate in water. So that's where the heat is. It's heating the solution. And as always, we ignore everything except the water. So if we've got 100 grams of water, we call the mass 100 grams, because that hasn't really got a very significant heat capacity in comparison to the water. So it would be inappropriate to include that. So that's equal to 100 grams for the M. C, as usual, is 4.18 and delta T is 1.30. So that's fairly straightforward this time, and that comes out to 543.4. And that, remember, will be in joules, because C was in joules per Kelvin per mole. Once again, we may as well now convert that into kilojoules, because that's what we're going to need later. So we divide by 1000, which is 0.5434 kilojoules. Okay, so now as before, we have to figure out how many moles of sodium hydrogen carbonate we had so that we can calculate kilojoules per mole. So for part C, we have moles is mass over mR, which is 1.07 grams, and the mR of sodium hydrogen carbonate is 84.0. And so if we calculate that, that comes to 0.01274 moles. So that's C. And then D, we have to calculate delta H. And this time, delta H is going to be plus the kilojoules divided by the moles. Plus because it's endothermic this time. And we know it's endothermic, obviously, because the temperature went down. So the sign of delta H is dictated by whether the temperature went up or down. So it went down, it's endothermic, therefore it's positive. So that's plus 0.0127, sorry, wrong way up, plus 0.5434 divided by 0.01274, which comes to plus 42.7 kilojoules per mole. Make sure that you put the explicit plus sign in. It's not just 42.7. Enthalpies have to have an explicit negative or positive sign. So plus 42.7 kilojoules per mole is your answer. So question 7, we have a neutralization, alkali plus acid, and you can see it's exothermic because the temperature goes up. And this time we're given the concentration and the volume of each substance. So first of all, it wants to know what was the total mass of the solution after mixing. So again, you think, well, it doesn't give us any masses, but remember, we can use this idea that the density of an aqueous solution approximates to the density of water, and that's 1 gram per cm cubed. So we can use that idea. So we get that the total volume is 50 plus 50 is 100 cm cubed. And then we use that idea that the mass in grams is approximately equal to the volume in cm cubed, just making the assumption that the density is close to that of water, which means that we have a mass of 100 grams is the first bit. And then it wants to know how much heat was calculated in part B. So usual thing now, Q equals mc delta T. So we've just worked out the mass is 100 grams, times 4.18 times 6.20 works out at 2591.6 joules. And as usual, we know that sooner or later that needs to be in kilojoules, so we can do that now. Divide by 1000 to get 2.5916 kilojoules is your value for Q. Okay, so next it asks us how many moles of sodium hydroxide were used in the experiment. So that just comes from the usual idea that if it's a solution, you think, oh yeah, moles is concentration times volume. We've got those two numbers, so it's concentration times volume in dm cubed. So that's 1.00, and it's 50 cm cubed, but remember that's got to be dm cubed, so you divide by 1000, so times 0.0500 is 0.0500 moles. Now, we've got to be careful here. That's the number of moles of sodium hydroxide that were added, but we need to worry about, is there an issue of excess here? But actually you can see that it's a one-to-one reaction, so equal numbers of moles will react, and you can also see that equal numbers of moles were added because we had the same volume of each and the same concentration of each, so obviously we've added the same number of moles of HCl. So neither of them is in excess because we've added exactly the right amount for them to react with each other. So the moles of sodium hydroxide added is also equal to the moles of sodium hydroxide reacted. But it was important to check that, because had it been in excess that would have affected the answer to the next bit. But what it asks us for is delta H for the reaction per mole of sodium hydroxide. So that's equal to minus, because it's exothermic. Remember, the sign is negative if it's exothermic. The kilojoules divided by the moles, which is minus 2.5916 divided by 0.0500, which comes to minus 51.8 kilojoules per mole is your answer for delta H. Okay, now we calculated this as an enthalpy change of reaction. We're saying, right, well, when the numbers of moles in the equation reacted, that's what the delta H would be. But what you can see is that that's also the enthalpy change per mole of water formed in a neutralization reaction. And remember, that's called the enthalpy change of neutralization. Okay, so that's a definition you've got to learn. It's the enthalpy change when 1 mole of water is formed in a neutralization reaction, and that's exactly what we've calculated here. So that's also equal to delta H of neutralization is the answer to part F. Now the next bit of the question looks at variations of this experiment where we change the mixture that was made, and what we're supposed to look at in each case is what happens to the temperature change as a result. So our answers are all going to be based on this, and we can just easily rearrange that. If we take the MC, we can slide it diagonally over to the other side to get that Q divided by MC is equal to delta T. Okay, so if we use that, we can then just look at which of those terms will change. So C is going to be the same because that's the specific heat capacity, and remember we treat that as always being 4.18 joules per Kelvin per mole if it's an aqueous solution. So it's really Q and M that we have to worry about how they change in the as a result of the things that we've done. So in the first experiment, the first variation, we're still using the same volumes because we've got 50 cm cubed of both solutions, but the sodium hydroxide concentration is only 0.5 moles per dm cubed instead of 1. So looking at that, so let's just write this again over here. So Q over MC is equal to delta T, and then we can look at what's changed. So M is going to be the same because we have the same total volume. Okay, because remember we've just said that the volume in cm cubed is equal to the mass in grams. That's what the approximation we're using, and we've still got 100 cm cubed of each, because the only difference is that we've now got 0.5 mole per dm cubed concentration instead of 1, but the volume hasn't changed and therefore the mass hasn't changed. On the other hand, because we're now only adding half as much sodium hydroxide, we can only get half as much reaction, if you like, half as many moles reacting, because we've only got half as many moles of sodium hydroxide. We'll now have excess HCl, but that doesn't help us, because if half of it doesn't react, then that's not going to contribute to Q. So basically Q is going to be half its original value, because only half as many moles of sodium hydroxide are reacting. So putting those two things together, the top line is halved, the bottom line stays the same, so the answer is halved. So that means delta T will be smaller, and more specifically we can say we predict it will be half its original value. Okay, so now in the second variation, what we do this time is add the same concentration of sodium hydroxide as before, still 1 mole per dm cubed, but we're going to add 100 cm cubed instead of 50. So bigger volume but the same concentration, so that's instead of the original 50 cm cubed. And the question is, what difference does that make? Well, the mass is clearly going to be bigger this time. Okay, so because our total volume is now 150 cm cubed instead of 100, so M is bigger, so 1.5 times bigger than the original. Just because we added the extra volume. But what about Q? Well, Q depends on how many moles react, and you can see that we've now added more moles of sodium hydroxide, but in the original experiment there was exactly enough sodium hydroxide to react with the HCl because we had equal moles of the two. So if we now add more sodium hydroxide, there's nothing for it to react with. So although we're adding more, the amount that reacts is the same because it's limited by the fact that all the HCl reacted in the original experiment anyway, so more sodium hydroxide makes no difference. So Q will be the same because the extra NaOH added doesn't react because it's all excess. Okay, so putting those two things together, you can see that we've now got the same top line, but we've got a bigger bottom line, and that means that delta T will be smaller. And again, we can predict quantitatively that it should be about 2/3 of its original value. But generally in these kind of questions, you can just say smaller or bigger, but the 2/3 comes from the fact that the total volume originally was 100, now it's 150, and 100 is 2/3 of 150. So that's where it comes from. But as I say, if you're not happy about the number, generally just saying bigger or smaller is all they would ask in questions like this. But you can see the crucial thing is setting out your thinking clearly. So make sure you know what the comparison is, which is why I've written it out there so that you can see what changed and what was and what was the same. Then write down the expression and say what happens to that term, what happens to that term. If you write it all down explicitly like that, these questions are not that hard. It's if you try and figure it all out in your head that you tend to come unstuck. Okay, so in the third variant of this experiment, we're changing the concentration of sodium hydroxide this time to 2 moles per dm cubed instead of 1. So that's the change. Instead of 1 mole per dm cubed. But we're keeping the same volume. Okay, so still 50 cm cubed, but now at a higher concentration. So this time you can see that M will be the same because we have the same total volume. Okay, because it's still 50 plus 50, 100 cm cubed, so 100 grams is our estimate of the mass. But what about Q? Well, again, it's this issue of excess, that by increasing the concentration of sodium hydroxide but adding the same volume, we're therefore adding more moles of sodium hydroxide, but it doesn't help because there's no more hydrochloric acid for it to react with. So all that extra sodium hydroxide is excess, and so Q is still the same. For the same reason as in the previous example, because all the extra NaOH is excess and therefore doesn't react. So if Q is the same and M is the same, then delta T is the same. And that's your answer.